An ideal step-up transformer steps 650 up to a higher voltage. There are 312 primary windings and 62,400 windings on the secondary. I don't even know if that's possible. There are 2.15 amps of current in the secondary. Ooh, tricky problem here. What is the voltage on the secondary, right? So we're going to go we're going to use V primary, V secondary is proportional NP and S, right? And our primary voltage is 650, right? Our number of windings is that. Our number of secondary windings is that. And you can solve for the secondary voltage, right? Notice that kilovolts is times 10 to the third, right? All right, so there's A. B says, what is the power passing through the transformer? Okay, well, to get power, you got to multiply. Power is IV, right? Whoops, that was an I that tried to be a V at the same time. All right, P is IV. Okay, so we've got the voltage in the secondary, right? And you could figure out what the current is in the primary as well, right? Okay, but I'm going to use the secondary, right? So the voltage is whatever this answer is, right? And then the current is 2.15 amps, right? And you'll get that there's a lot of watts, right? Remember, a kilowatt is times 10 to the third watts. All right, what is the current in the primary? All right, so to do that, you're going to go for an ideal transformer, right? The power in equals power out. Okay, don't get mad about it. All right, so power in is power out, right? Okay, so we know the voltage now in the secondary. That's your 130 kilovolts. The current is 2.15. We know the voltage here is 650. So now you can figure this out, right? All right, let's see. Current in the primary. Some transmission lines have a resistance of 4 ohms. How much power is lost if you transmit 10,000 watts of power at 650 volts and then at 330 kilovolts, right? Well, so the way to do this is the same way, right? For D, okay, and I'll show you how to do it for like 650 volts, right? The first step to do is to figure out the current. The current is going to be power divided by voltage, right? P equals IV, so I is P over V, right? So figure that out. You've got 10,000 watts, right? And 650 volts, and that's kind of a lot of current, right? So figure out that current. It's a big number, right? And then the power lost will be I squared R in those power lines, right? So take that current that you just figured out. It's a big number. Multiply by 4, and you'll get 947 watts, right? Okay. Then do the same exact thing for 330 kilovolts, right? Okay. 10,000 divided by 330,000, right? Is going to be a tiny little current, right? And then do the same thing, I squared R, where R is 4 ohms, right? 4 ohms, there it is. Okay. Do the same exact calculation. You'll see that it's just not very much power. And this is why they use super high voltage lines, is to reduce that current so that this power loss is less, right? So why do we transmit it, right? Which is interesting, right? Because that makes the power lines much harder to insulate and much more expensive to build, but over the long haul, over long periods of time, you save so much money because you're wasting less power. Okay, so why do we laminate the cores of transformers? So what we're talking about, a laminate is if when you looked at those transformers, right? Whoops. Come on, baby. Let me go to the side. Okay, so here's a transformer. Here's our primary, right? Here's our secondary. In this case, there's a lot more of those than those, right? Okay. Think about this piece of metal here, the iron. You have to use the iron because iron lets the magnetic field, basically creates like a magnetic circuit. The magnetic field lines are going this way and this way, okay, depending, on the cycle of the current, right? Okay. If you looked at it from this side here, let's look at it from this side there. right? If we're looking down on this core here, you would have a chunk of metal inside these coils of wire, right, that are wrapped around it like this, okay? Well, think about it. The magnetic field is changing back and forth 60 times a second. You would get absolutely crazy eddy currents, okay, in this thing. Let's imagine that we're creating a magnetic field upward in the page. Well, currents would flow, electrical currents, not magnetic, in quotes, current, right? But actual electric currents would flow to oppose that change in flux. And you kind of want the flux to change. You don't want these currents to oppose it. And besides, they would create heat. These little electric currents would flow like that. So what they do is they take this this conductor, this piece of metal, and instead of making it out of a piece of metal that can conduct electricity, they insulate it. They make it into little slabs like this, like that. And these are insulated from each other, so the magnetic field can exist, but the currents can't flow because there's not a big path for them to flow. So why do we laminate them? To reduce this eddy currents that would naturally arise in a transformer and heat up the core. So you reduce the inductive heat loss basically in that core by laminating it so that electric current has a very tiny path to follow. Therefore, they'd be, I guess, smaller. I don't know. I'm not a material scientist, so I don't know that part. But anyway, yeah. All right. Good luck. Go get them.